right, now that we know about the right triangle trig functions, we can do some applications, which means word problems, which means where math becomes very, very practical. So this is kind of terrific. First, we need to know what an angle of depression is or what an angle of elevation is. And so on your worksheet, there's this little picture here. There's a horizontal line here. And so very simply, an angle of elevation is from the horizontal looking upward. So here's the horizontal, and if we're looking upward, this would be an angle of elevation. But if you're standing right here and you're looking down, you're looking downward, this right here would be called an angle of depression. So, what an angle of depression is, it's an angle from the horizontal downward. And an angle of elevation is an angle from the horizontal. It's an angle from the horizontal upward. So now we've got 5 little examples we're going to go through and see different ways that these can be used. Okay, so the first example is on your worksheet, and I'll just read it in case it might be kind of hard to read. And there's this nice little picture, but it's pretty cool because they do this in real life, and it's a very real application. It says to save time or because of the lack of landing facilities for large jets in some parts of the world, the military and some civilian companies use air-to-air refueling for some planes. So they give us a picture of 2 planes refueling. It says if the angle of elevation of the refueling plane's hose is 32 degrees and B in this figure is 120 feet, how long is the hose? So here you're going to get to see that I have no ability to draw anything at all ever. So here's my pictures. I've quit trying to draw planes. This is the first plane and this is the second plane because it's just crazy. So what we have here is the fuel line coming from one plane to the other. So I will just draw the hose that's going to refuel. So this plane right here is trying to refuel this plane right here. This one's refueling this one. And this is the length of our hose. And so it says that it has an angle of elevation. So this is the horizontal, and we're looking up to this other plane. Our angle of elevation here, they say, is 32 degrees. Here, okay. And then they drew this nice little triangle for us, and they said, this is coming down here. This is our 90-degree angle. Oh, I made that too big. This is 32 degrees. And they said that B, this length from here to here of this triangle is 120 feet. All right, that is all the given information. So what they said is, how long is the hose? In other words, what is these? So if we remember our little triangle, if we call this angle C, right? We could call this hypotenuse C. This could be angle B, this could be angle A, and this could be little a. That's our triangle that we saw. But basically, we need to figure out what C is, and we have this angle. Can we think of a trig function that involves this side, which we know, 120 feet, the adjacent side, and the side we don't know, hypotenuse, adjacent hypotenuse. Adjacent over hypotenuse is cosine. Think of SOHCAHTOA. So cosine, the cosine of theta is adjacent over hypotenuse. So in this example, the cosine of 32 degrees is adjacent 120 over hypotenuse, C. I'm going to kill my fraction. C times the cosine of 32 degrees is equal to 120. Now we'll just divide by the cosine of 32 degrees. And we can solve for C. And when we do that, we find that C is equal to 141.5 feet. And so we can write a sentence. The length of the hose, the length of the hose is 141.5 feet long. So there we go. Let's do example 2. Example 2, there's no picture, there's just some words. So that's fine. We just draw our own picture. And you don't even have to know how to draw to do a picture. So, find the angle of elevation of the sun at the moment when a 21-meter flagpole casts a shadow of 14 meters. All right, so we have a sunshine. Here is our sun up in the sky. And we have some flagpole. Maybe I won't make it red too. We'll make our flagpole. Here is the ground. Here's the ground. Here's a flagpole. Here's my flagpole. Here's my flag. So, it says the sun is hitting this and it's casting a shadow. So on the ground, it's casting this little shadow right here. Okay, now, what it says is the angle, find the angle of elevation of the sun at the moment when the 21-meter flagpole casts a 14-meter shadow. So this says the flagpole, they told us how tall he is, 21 meters. They told us how long his shadow is. His shadow is 14 meters. Then they say, find the angle of elevation. So angle of elevation means from the horizontal looking up. So over here is the horizontal and we're looking up at the sun because the shadow is going to be cast this way. So the angle of elevation is going to be whatever this angle is. I'm going to draw it like this. This is not to scale, but this is the angle of elevation that we're looking for. So what we know in terms of this angle is the side opposite and the side adjacent. So is there a trig function that involves opposite and adjacent? And there is, and it's called tangent. And so the tangent of angle theta is equal to opposite over adjacent. And you can put the meters, but those will cancel out. This is just a value. How we get the angle is we have to use the inverse button on our calculator. So we're going to take tangent inverse of both sides of this. Tangent inverse of this value. These cancel each other out because it's a function and it's inverse undoing each other. And we get that theta is equal to the tangent inverse of 21 over 14, or that theta is equal to 56.3 degrees is what we get right there. So that is example 2. We've got 3 more examples, and then we're done. So let me erase some of the stuff, and we'll look at these 3 examples. The next one is about, what is this one about? Oh, a lighthouse, okay. And the next one's about a boat, and then the last one's about the space shuttle. So that's kind of cool. I missed the space shuttle, but I understand that it was probably time to do something different. But anyway, one time I got to see it lift off a few times, which was pretty cool. But one time I got to see it re-enter, and that was, I think, the coolest thing I've ever seen. It's just coming in from outer space and it re-entered. That's kind of pretty fun. Okay, here we go. Example 3. From the top of a lighthouse 21 meters high, a sailboat is sighted at an angle of depression looking down at 6 degrees. How far from the base of the lighthouse is the boat? All right, so again, I can't draw, but here's my lighthouse. Let's see, it's got some kind of bulb in it. Some kind of lighthouse. Here's how you know this is a lighthouse. It's got some kind of stripes on it. Okay. There's my lighthouse. Okay, out here is the sea. Out here is some boat. There's my sailboat. Okay, so, let me try harder. I don't know. This is the lighthouse. I don't know what's happening there. Okay, there we go. Now, it says, from the top of a lighthouse 21 meters high. Okay, so they told me this height is right here to here is 21 meters high. Okay, that's important. A sailboat is sighted at an angle of 6 degrees, of a depression of 6 degrees. How far from the base of the lighthouse is the boat? How far is this distance? That's what we don't know. And they told us that from here, this horizontal, looking down. So this is the horizontal, looking down is the boat. And so this is not to scale, but they told me that this angle from the horizontal looking down is 6 degrees. Real quick, here's a real quick reminder of something you probably saw a long time ago, maybe in middle school. So if you have two parallel lines and they're crossed by something called a transversal, there are a whole bunch of angles that are equal. This angle right here is equal to this angle right there because those are called vertical angles. But also, this angle right here is equal to this angle right here because these are called alternate interior angles. That's another reason those are equal. Let's do x's. This angle right here is equal to this angle right there because those are alternate interior angles, and this is equal to that one because that is a vertical angle. We can go on. This one is an x, vertical angle. This one is a dot, vertical angle. And then there's something called alternate exterior angles. Those are equal, and those are equal. So I say all that to kind of remind you about that because right here, you see the 6 degrees right here? This horizontal is parallel to this horizontal, and this is being crossed by a transversal. So this angle, 6 degrees, is equal to this angle, so this is also 6 degrees, although it doesn't look like 6 degrees in my picture. It's okay. This is my 90-degree angle, and I can figure out what this angle is by subtracting it from 6 from 90, which is going to be 84 degrees. Okay, I have this triangle. What I need to know is x. So is there a trig function that involves adjacent and opposite? And there is, and it's called tangent. So I can do 6 degrees. The tangent of 6 degrees is opposite 21 meters over adjacent x. We get x times the tangent of 6 degrees is 21. Divide by the tangent of 6 degrees. And we can get that x is equal to 200 meters, about 200 meters. Let's write a sentence. The sailboat, not sailboat, the boat. I just drew a sailboat. The boat is 200 meters from the base of the lighthouse. Just like that. All right, good. Let's do the next example 4. This one involves a little bit of algebra, but that's good for us to know how to do algebra. So here we go. This was 3, 4. All right. This says a boat is cruising along the coast on a straight course. There is a rocky point sighted at an angle of 31 degrees from the course. After continuing 4.8 miles, another sighting is taken and the point is found to be 55 degrees from the course. How close will the boat come to the rocky point? So, we have a nice little picture, but this is what's happening. There is some rocky point out here that the boat does not want to run into. And so it takes a reading. It's out here on the water. This is all water. But he's here sailing. Here's my boat. And he looks up here and says, how far, what is this angle right there? And they take a reading. And right here it's 31 degrees. Okay. And so then they travel further. And how far they travel, they say, from here to here is 4.8 miles. Good. And then they take another reading. What is this angle right here? Now the angle has increased to 55 degrees. And so ultimately they want to know how close, if they keep on this course, how close is this boat going to get to this rocky point? So you don't want to get too close because it could tear up the boat and it could sink. So really what we want to know is, what is this distance here? What is this distance here, y? What is y? That's what we're after. What is y? This is my rocky point. I'm going to label that because really I can't tell from what I drew what this is supposed to be. It looks like, I don't know what that is. So this is what is y? That's what we have to figure out. And so what's missing, if we knew this whole distance, this would be pretty simple, but we don't know this distance. So this is an unknown thing we don't know here. So we got to work with what we have, and we have plenty. We can figure this out. These are two right angles. Do you see this? Here is one big triangle. This one, y is here. 4.8 plus x is here, and this is 31 degrees. And then here's another right angle. 55 degrees. This is x. This is y. And so we have this one to work with, okay? So since we have two variables we don't know, x and y, we need to come up with two equations separate. And if we have that, two equations and two unknowns, we can solve this. So when I look at this first triangle, we have opposite and adjacent, and that says tangent to me. And when I look at the second triangle, we have opposite and adjacent, and that also says tangent to me. So let's write two tangent ratios. So we say the tangent of 31 degrees is equal to opposite y over adjacent, 4.8 plus x. And the tangent of 55 degrees is equal to opposite y over adjacent x. So let's solve this. We have two equations and two unknowns. What I'm going to do here is just kill my fraction by multiplying both sides by x. So I get x times the tangent of 55 degrees is equal, these cancel, is equal to y. All right. Now, I'm just simply solving. I'm going to solve by substitution. You've done this in intermediate algebra a long, long time ago. This is where you can solve a system of equations by substitution or elimination. I'm just using substitution here. Y is equal to this. Okay, I got it from this equation. I'm going to substitute this in here for this y, and then I have one equation all in x. So it looks like this. The tangent of 31 degrees is equal to y, but I'm going to replace that with this value, x times the tangent of 55 degrees over 4.8 plus x. And I'm going to solve this equation for x. So this might be a little bit daunting, but I'm going to show you how. Kill your fraction by multiplying both sides by the denominator. So on this side, I'm going to multiply by 4.8 plus x over 1 times, on this side, 4.8 plus x. I've multiplied both sides of the equation by the same thing. That is legal. This will cancel out. I'm left with x times the tangent of 55 degrees. I have over here 4.8 plus x times the tangent of 31 degrees. But what I'm going to do is free up my x here by distributing the tangent of 31 degrees to both sides. Now don't freak out. The tangent of 31 degrees is just a number. It might be a sloppy number, not a whole number, but it's just a number. So if this was just a 31 times this, you would distribute the 31. I'm going to do the same thing with the tangent. So what I'm going to do here is I'm going to distribute this number to both sides. So this will look like this. 4.8 times the tangent of 31 degrees plus x times the tangent of 31 degrees. Now, what we have to do is solve for x. This is just a linear equation. Pretend for a second, just in your mind, think, oh, what if I didn't have all this tangent business, but I just had this equation going on? Here's my pretend over here. What if I had 4.8 plus x equals to, what if I had 4.8, what if you take out the tangent, times 31 plus 31x is equal to 55x. If you had this equation right here, what would you do? What you should do is get all the x's on the same side. I would subtract 31x from both sides, and I would get this number, 4.8 times 31 is equal to, what's that going to be, 24x, and then I would divide by 24. Well, that's not what I have. I'll have all this tangent, but I'm going to treat it the same way. Get all your x's on the same side of the equation. I'm going to subtract this from both sides. So now I get 4.8 times the tangent of 31 degrees is equal to x times the tangent of 55 minus x times the tangent of 31. Now, I would just add these if they were whole numbers. They're not whole numbers, so this is a move that you can learn to do, and it's a good thing to know how to do. Factor out an x, so you just have one x. So this could be x times the tangent of 55 degrees minus the tangent of 31 degrees times 4.8 times the tangent of 31 degrees. This is a number. This is a number. I'm going to divide both sides by the number that's beside my x, just like I would divide both sides by the 24 right here. Divide both sides by the tangent of 55 degrees minus the tangent of 31 degrees. Those cancel, and I get that x. When I put this in my calculator correctly, make sure you put parentheses around this in your calculator, is equal to 3.5 miles. When you round, I think you get 3.5 miles. Now, did I answer what they asked me? Not yet. What they asked me was, how close will the boat get to the rocky point, which means what is y? So I still have to solve for y, but look right here. Y, if you can still see this, y is equal to x times the tangent of 55 degrees. So y is equal to x times the tangent of 55 degrees. And when you put that in there, you get that y is equal to about 5. Okay, let's write a sentence. The boat will come within 5 miles of the rocky point. All right, one more example and then we're done. The last one is about the space shuttle. It's pretty cool. So, and it's not a long one. We have the space shuttle coming in from outer space. So now we have SpaceX. And so they have been landing they brought, who was it? It's not Bill and Doug, it was Doug and, I forgot the two astronauts who went to the space station and came back. That was pretty exciting. Now SpaceX, and they like dumped them in the ocean and recovered them that way. So we don't have anything as dramatic. Well, I mean, that's pretty dramatic, but we don't have the space shuttle re-entering. But still, pretty cool. Here we go. Let's look at this example. Okay. Example 5. It says, at the beginning of the final approach, the shuttle is at an altitude of 3,600 feet, and its ground distance is 9,300 feet from the beginning of the landing strip. What glide angle must be used for the shuttle to touch down at the beginning of the landing strip? So, we have the space shuttle coming in from outer space in the olden days, and it's going to turn around, and like when it comes around here, it's going to make his final approach. Okay, so here's his final approach. He's getting here, and he's going to say, okay, here I am, and I have to land. Here's the landing strip right here. So what the question is, they say, we're going to start to label some stuff. It says, if at the beginning of the final approach, so we're going to call this the beginning of the final approach right here, the shuttle is at an altitude of 3,600 feet. So that means from here to the ground is 3,600 feet, okay? And its ground distance is 9,300 feet from the beginning of the landing strip. So this is the beginning of the landing strip. So from here to here is 9,300. All right. It says What glide angle must be used for the shuttle to touch down at the beginning of the landing strip? So, if this is our shuttle, right? Here's the horizontal. This is an angle of depression. This is his glide angle. What is his glide angle? What is this angle here? That's what we got to figure out. Right there. Is that right? No. I wrote this in the wrong place. This is his glide angle. That's theta. And so, not this. This is the glide angle. Glide angle. But remember, two parallel lines crossed by a transversal, their alternate interior angles are the same. So this is also theta. This is what we're after right here. That's our glide angle. Well, this is a very simple matter of trig. What trig relationship involves opposite and adjacent? And that is tangent. So let's see. The tangent of theta is 3600 over 9300. And so what we're going to do is we're going to take the inverse, or the arctan, of the tangent of theta. I'm just knocking off, I'm dividing these by 100 to make it, I don't have to write as much. The inverse function of a function, these undo each other. We just have theta is the tangent inverse of this ratio. When you put that in your calculator, you will find that theta is equal to 21.2. We can write a sentence that says the glide angle that the shuttle should use upon approach to the landing strip is 21.2 degrees. All right, there we go. Some right triangle applications.